Okay, welcome. Today we'll be talking about Lesage gravity, which is some really cool thoughts on gravity from someone in the 1700s that have been sometimes reinvented today. So we'll be getting to that. It's pretty interesting. First, I'll say that this is Physics X, Extraordinary Concepts in Physics, which is being taught at Michigan Tech. It's a class about the concepts of physics, like Lesage's concept of gravity. And I'm trying to go heavy on concepts and light on mathematics. So I'm trying not to use a textbook. You can find, there's Wikipedia links every lecture. There's at least 25 lectures online now, mini lectures, 15 minutes. You can find them if you can read this. You can go to this address and find them on the web, or you can search for Starship Asterisk on Google, and then after that, search for Physics X, and you'll see a lecture list. So as I like to do, I'll start with a bit of a quiz about gravity. Is the mechanism for gravity known? So you can think about that. The answers might be yes, it's the changing geometry of space-time. That's what Albert Einstein said, right? So that solves that. No, gravity still requires action at a distance. Or maybe and sometimes, if you don't want to commit yourself, just want to get sort of in the middle, maybe you can be right a little bit, you might want to go with the maybe and sometimes answer. All right. So I will quote one of my favorite physicists who had a lot of great things to say about physics and what we know about physics and teaching physics. There is no model of the theory of gravitation today other than the mathematical form. So there are several mathematical forms. So one, probably the most useful one for our solar system and for satellites around the Earth, is Newton's law of gravity, which just goes that the force of gravity is equal to g, one mass times the other mass divided by r squared. Almost everything in the solar system can be solved with that simple equation. There are things, though, if you look closely, you can find discrepancies. And those discrepancies were annoying. And they were, as you know, essentially solved by Albert Einstein in the early part of the 20th century, the 1900s, with the advent of the general theory of relativity. And the equations of general relativity can be interpreted as geometrical equations. So geometry changes, and that's why things move. However, why does the geometry change? You can keep asking the whys. And also, what about action at a distance? If you take away the sun or something like that, what would happen here? That doesn't explain everything. So general relativity also, when you get down to high energies, very small length scales, general relativity doesn't have answers there either. So general relativity is a better theory of gravity than Newton's theory of gravity. However, so far, we can write down the equations, and so even when the equations apply, we're not always exactly sure why they apply. There have been attempts to come up with mechanisms of gravity, and one dates back to the 1700s, mid-1700s, by a French physicist, Lesage. I hope I'm pronouncing it correctly. I only see it. I don't really hear it said. Now, when I was a graduate student, when I stumbled onto this as a parenthetical phrase in one of the books I was reading, I just thought this was the greatest stuff since sliced bread. I thought maybe it could be made to work. I thought it was really interesting. I've tried to find out everything I could about it. I even made a brief presentation to my friends and whatever faculty would come when I was a graduate student. But so now with Wikipedia, we can find out more about it than I ever knew right here on the web. Most people don't know to look, though, but it's really interesting stuff. I have since found out from Wikipedia that there was an earlier attempt that even Lesage himself didn't know about for a while by someone named Fatio, I believe his name is. Lesage gravity is interesting because it does have some, even today, there are actually some relevances to modern astrophysics, and if you look at it in just the right light, you might see that it shares some attributes with virtual quantum forces. So, what is it that I'm talking about, all this buildup? Okay, first, before I tell you what it is again, I'll tell you even more about it. Lesage gravity is not the final answer to gravity. It has problems. There is no classical formulation of it that works. It has never been accepted for a serious mechanism of gravity, however impressed you are with the next several slides. It is occasionally reinvented today by people who don't know its history or flaws. Sometimes I've heard there are meetings where people get together and discuss it like it's new and different, which is good in a way, but eventually if those groups were to mature, they would realize that there are things that it can't do, and eventually they would merge with mainstream physics. However, I said it does remain useful as a toy model for thinking about gravity. Sometimes I think about gravity using the Lesage model. It helps understanding particularly some classical Newtonian problems, and its mock gravity is very similar to it in some physical situations, and I'll talk about that a little bit in the next few minutes. So here's the basics. The universe is filled with lots of unseen particles, and they've been named different things by Lesage and Fatio, but everywhere there are these particles just zipping around. They go everywhere at all times. And so the room is filled with these particles. We just don't see them. However, let's say we put down an object here. Let's say this object is opaque to the particles. Then another object over here, say, would not see this red particle. That would have been absorbed by the lower one. And so this upper object would be getting hit by particles in all directions, except from the direction of the other object, which would be either absorbing or doing something to the particles. So this guy would feel a force toward the other guy. And since the situation is identical, this guy would feel a force to that guy. So all you have to do is put down two objects that are capable of, say, absorbing these particles of which we don't know what they are, and you can get forces toward each other. Interestingly, it doesn't depend on the body's shape. What we're seeing is essentially a shadow effect. It will cause a mutual attraction. So this works if particles, here's an old-time rendition of it. This works if objects are mostly empty space. So it turns out that if you used optical light for your corpuscles that go everywhere, that fill the universe, and you have two, let's say, billiard balls, then one billiard ball was highly dense and the other one was fluffy and light, then you would expect that Lesage gravity would say there would be an equal acceleration of each ball to the other because they're blocking the same amount of light as long as they're opaque on the outside. So that's why Lesage was aware of this, and he said, well, objects are mostly empty space, which is right. So if you make things mostly empty space, and there's little things, he didn't know about atoms, but if we have atoms in there or something, or nuclei that don't block each other, then you get back to the right amount. And so if scattering is somehow unimportant, if absorption is unimportant, then you can get an inverse square law that looks just like gravity. And now you have a mechanism for gravity. And that's really cool because back in Newton's day, Newton understood that this was action at a distance, and it kind of troubled him. Einstein troubled him as well. But if this is right, maybe the troubles are gone. So let's look in some more detail here. There are some problems with this. This was analyzed by many of the great physicists between when Lesage suggested this, including Newton and James Clerk Maxwell and Einstein. The masses must be almost completely transparent to these ultramundane corpuscles, as the name was by Lesage, which isn't a big problem. But you can't have overlap. You can't have whatever they are overlapping each other because we don't see overlap. So far as we can tell, mass, if you put one mass next to another mass, there's no shadowing effect. One of the problems I alluded to is that what happens when a particle hits an ultramundane particle or something, whatever it is that's creating this force? What happens when it hits one of these things? Is it deflected? And if you find out that it's just reflected, so it's just a straight reflection that comes off in this direction, then you get a problem. You don't get an exactly inverse square force anymore. And then if you start looking at the solar system and even large massive balls in the laboratory, you're not getting the correction term on r squared that you would expect. So you can't have these things just be reflected. Well, another possibility is, let's just have them absorbed. They're not reflected, they're absorbed. If that's true, and you then can attribute these things to have some kind of energy, you find out that pretty much anything in the room would explode on pretty much short order. It would just soak in that energy and boom, it'd be gone. So you can't have them absorbed. You can't have them reflected. You can't have them absorbed. There's also a drag force of these things, and the way these corpuscles were defined, there was not external evidence of them, particularly before. So you can map this, though, into virtual particles, of which there is no quantum theory of gravity, so it might not necessarily work for gravity, but you might try to play games like this with electricity and magnetism, but then this is pretty much everything has to be attractive, so it doesn't work so much there either. But were there a quantum theory of gravity, it might share some conceptual framework with this. All right. Other problems, here's more problems. I'll point this one out, aberration. So we talked on a previous lecture about speed of gravity, where a lot of things, where you can look up the speed of gravity lecture. Aberration was considered a lot there. So if you have the sun over here, and we'll make the sun yellow, and then you have the Earth, which is the blue planet over here, and it's going around the sun, then in special relativity, you get things appear to move toward the center of your frame. So the sun would appear up here more. But now if there are all these particles flying through space, you would get an attraction ahead of you, which would mean that you would actually speed up. And if you sped up, my guess is you would probably be ejected from the solar system. You can't have stable planets. So even if you start playing games with that, it's hard to match the moon's motion. The moon's motion around the Earth is characterized by extremely good measurements, as we have laser reflectors on the moon that can tell us the distance to less than a centimeter at any time. A lot of observations of the moon. We know pretty much where it is. So in order to get the exact position of the moon takes quite exact theories, and there are hundreds of correction terms due to things like Jupiter and stuff like that. And whenever people try to make Lesage come up with the moon's orbit, you just can't. It's just so complicated you can't get it right. All right. So, however, Lesage gravity is useful for visualizing things. For instance, let's say you put in a particle here inside a sphere that's constant. You know it's a sphere because it has the window on it. So it can be anywhere in this sphere, and the sphere is constant thickness. So the way I think of this is, so long as the sphere is a constant thickness, I can just think of Lesage particles creating gravity toward that sphere, and it seems more intuitively obvious to me that this particle is not attracted to any place inside that sphere. That inside a constant shell of mass, where it's the constant thickness of shell, you're not going to get acceleration toward anything. And picturing it with Lesage gravity helps me to visualize these things. So in other things, I found it useful to, even though I know it's not the complete theory of gravity, especially when doing Newtonian calculations, to try to picture things in a Lesage sense. And last, Mach gravity is a distant cousin of Lesage. So let's say you have a photon field. Let's say early in the universe, just optical light is everywhere. And now you have dust grains, which we know are opaque to optical light. It turns out the dust grain, people hypothesize that even galaxies, but we'll stick with dust grains right now, are attracted to each other. They really are, because of the photon field that surrounds them. It causes what's called Mach gravity. And Mach gravity is very similar to Lesage, but it doesn't create real gravity. It's just another term based on light in the photon field that causes an attraction. Lesage himself was not a complete crackpot, lest we laugh at him. He developed an early version of the electric telegraph in 1774, which might be considered a predecessor of the internet. It was relatively crude, however, because it only connected 2 different rooms, and it had 26 wires strung between the 2 rooms, 1 for every letter. So our current internet is a little more sophisticated, but that was pretty good for 1774. And with that, I will leave you toward next time. See you next time.